Let's begin with a simple thought. Have you ever noticed how students pick seats in a classroom? The first row fills up, then the next, and it goes on. Electrons and atoms behave the same way, they don't just float around randomly. They occupy defined spaces called energy levels or shells. After the discovery of electrons, the next question was where exactly do these electrons reside inside the atom? To answer that, Bohr and Bury gave a set of clear rules that explained how electrons are distributed. And these rules form the basis for understanding chemical bonding and the behavior of elements. Imagine concentric layers surrounding a nucleus. These are energy levels or shells. The one closest to the nucleus is called the K shell, labeled as n equals 1. The next is the L shell, or n equals 2. Then comes the M shell, which is n equals 3, and so on. As the shell number increases, the energy of electrons in that shell also increases. But here's the catch, electrons fill the lowest energy shell available first. On screen, you see figure 4.3, which shows these energy levels, each one like a seat waiting to be occupied, starting from the innermost. Now, how many electrons can each shell hold? That's determined by a simple rule. Maximum electrons in a shell equals 2 into n squared, where n is the shell number. So, for the K shell, where n is 1, 2 into 1 squared gives 2 electrons. For the L shell, n is 2. 2 into 2 squared gives 8 electrons. For the M shell, n is 3. 2 into 3 squared gives 18 electrons. For the N shell, n is 4. 2 into 4 squared gives 32 electrons. This rule tells us the upper limit of electrons for each shell. No shell can exceed this based on its value of n. But electron filling isn't just about maximum capacity. The Bohr-Bury scheme explains the order of filling. First, electrons always fill the innermost shells first. You can't jump to the third without filling the first and second. Second, even if a shell can hold more by the 2n squared rule, the outermost shell can have a maximum of 8 electrons. That's because atoms seek stability, and having 8 electrons in the outermost shell is often the most stable configuration. It's called the octet rule. Noble gases like neon and argon are unreactive precisely because their outermost shells are full. Let's apply what we've learned using real examples. Take hydrogen, atomic number 1. It has 1 electron, so its configuration is 1 in K shell, written as 1. Now carbon, atomic number 6. Electron distribution is 2 in K shell and 4 in L shell, spoken as 2 is to 4. Next is sodium, atomic number 11. It has 2 in K shell, 8 in L shell, and 1 in M shell. So we say 2 is to 8 is to 1. These electron configurations not only follow Bohr-Bury rules, they help us understand valency, bonding, and periodic trends. You can see these visually represented in figure 4.4, showing the structure of the first 18 elements. So why does electron arrangement matter so much? Because it's the foundation of how atoms behave in chemical reactions. Atoms with full outer shells, like helium or neon, are inert or non-reactive, but atoms with incomplete outer shells will lose, gain, or share electrons to become stable. That's the beginning of bonding. The Bohr-Bury scheme gives us a practical rulebook to predict this behavior. From metals reacting with acids to the salt in your food, it all begins with where the electrons are, and understanding this distribution helps us predict reactivity, build chemical formulas, and explore the periodic table. To sum it up, electron distribution in shells isn't just an academic idea. It determines whether an element explodes in water, glows in neon signs, or sits inert like argon. With the Bohr-Bury rules and the 2n squared formula, we now have the tools to explain how atoms organize themselves and why they react the way they do. I hope this session helped you see how something as tiny as an electron holds the key to the chemistry of the world. Catch you in the next class with more insights into the invisible yet powerful design of atoms.